This talk is aimed at people who have heard of Rust. So like maybe you've heard that Rust is a safe systems programming language. Like it can do the things that C and C++ can do, but it also doesn't have like seg faults, use after free, dangling pointers, things like that. Maybe you've heard that. Maybe you've even got a chance to try a little bit of Rust programming, but you haven't gotten to the point where the language really clicks. Maybe you're interested in learning more about how the language does what it does and what these safety rules mean for the language. That's who this talk is aimed at. And I think for most people, getting Rust to really click, it takes about a week, or maybe several weeks, and it takes a while. Rust has a bit of a learning curve. And so my goal here is to try to compress the most important ideas in getting Rust's story to click into an hour, which is pretty aggressive. So to do that, I'm going to need to make an assumption. I'm going to need to assume that you understand some C++. You don't have to know all of it. Right? I'm not a C++ expert. I'm sure I'm going to make that evident at some point. But if you know what constructors and destructors are, that's good. If you know what a move constructor is, that's awesome. That's about all we'll need. I'm going to assume that knowledge, and that's going to let us zoom right to the big ideas, right to the most important things that make Rust different. And then we can talk about those within an hour. And it's still going to be aggressive. This is aiming to be a fast-paced, maybe even difficult talk, but I'm going to try to cover a lot of ground. I'm also doing an experiment here. What I've done is I've recorded this talk already once, more slowly. So there's another recording that I will link to in the description. I'll also link to the slides. And the first recording is much longer. So the first recording is like 2.5 hours. And I go through the same slides, much more slowly, and trying to give all the detail, maybe not assuming quite as much knowledge of C++. Might be a little bit easier for C programmers, for example, to follow. But I think 2 hours, 2.5 hours is a bit too long. So I'm trying to make this talk fit in an hour. So this is going to be the fast version. You're watching the fast version. So here we go. So obviously we cannot possibly cover like all of Rust, even most of Rust in an hour. That would be ridiculous. The goal is not to get to the point where we could write Rust programs in an hour. We can't do that. We're going to have to skip over most of the language, right? Including, for example, syntax, right? Like we're not even really going to talk about syntax much. The goal is to use side-by-side examples of C++, which we understand, and Rust, which is doing the same thing, to allow us to sort of reason about the Rust code without worrying about the nitty-gritty details. Well, without worrying about most of the nitty-gritty details, because we want to focus on the big ideas. And there are 3 that I'm going to focus on: references, mutable aliasing, and move semantics. And we're going to kind of glide over and push aside all the rest, and these are really important topics that we're not going to talk about, right? We're not going to talk about enums. We're not going to talk about error handling, right? How do you handle errors? That's pretty important. We're going to kind of skip over it. And the story here is that some of these things will be pretty familiar anyway. So for example, generics like templates, like if you know C++ and you know the angle brackets and you can put T in there, you'll see generics in Rust, and that'll make sense. Or error handling, you can kind of learn that as you go. It's not going to be very confusing when you see it, but some of the big ideas are confusing and are a little bit harder to learn as you go. That's what we're going to try to sort of laser in on, go right to those 3 big ideas. So let's get right into it. 2 of them right off the bat, right here on this slide. This is going to be the last wordy slide, and then we're going to get right to code, looking at some code and see what happens. So the idea here is got some familiar stuff on top, and then we're going to have 2 big new ideas below. So the familiar stuff, right? You have 2 pointer types, right? 2 primary pointer types, right? And then in C or C++, you would call those const and non-const pointers, right? In Rust, we're going to call those shared references and mutable references. The syntax is a little different. We say ampersand T instead of T star or const T star. We say ampersand mute T, what I'm going to call ref mute T. For the mutable reference. But the idea is the same. They behave like pointers. When you want to dereference one of them, you use the star operator. So they're going to look familiar a lot of the time. And there's sort of like we're used to, there's these 2 types. And the shared reference which is like a const pointer, you're usually not allowed to modify things through it. And the mutable reference, of course, you are allowed to modify things through it. So that much is pretty familiar, coming from C, coming from C++. And same story here, right? These are just pointers, right? There's no garbage collector. Having a pointer to something doesn't magically keep it alive. And so when we take pointers to things, we do have to worry about how long those things live, right? And so if we were to retain a pointer to something that's gone out of scope, in C and C++, that would be a use after free, right? That's bad. That's undefined behavior. In Rust, here's big idea number one. We just can't do that. So in Rust, references always have to be valid. You can't construct a dangling pointer. You can't construct a null pointer. If you try to retain a reference, or what we might call a borrow, to some object that's going out of scope, and you try to keep using that reference, Rust is not going to compile your program. So that's big idea number one. References are always valid. Big idea number two, mutable references are unique. So we're not allowed to do any mutable aliasing. So what that means is if I take a ref mut t, a mutable reference to some object, that has to be the only reference to that object while it's alive. There can't be any other ref mut t's to the same object. There can't be any other shared references either. So when I have a mutable reference to something, that can't be aliased at all. There can't be any other borrows of that thing. That's big idea number two. That's very different from C++. C++ is happy to allow mutable aliasing. So we'll talk about some examples for number one first. We'll see some examples of that. And then we'll talk about number two. We'll see some examples of that. That's going to be the first almost half of the talk. So here we go. Let's look at some code. Big idea number one. So here is what I'm hoping is a pretty familiar sample of C++ code, right? This is sort of the simplest way to create a dangling pointer, right? Where this is what we're not supposed to do, right? What do? We have myint is 5. We take a pointer to it, but myint is going to go out of scope at the closed curly, right? I can use my mouse at the closed curly brace. Myint goes out of scope. We've retained myint putter, which is declared in a longer lived scope. And when we try to dereference it, that is a use after free or a dangling pointer or whatever we want to call it. Skip ahead. If we look at what address sanitizer calls it, it's a stack use after scope. So if we run this code under address sanitizer, it's going to complain at us and make noise. We're not supposed to do this, right? And this should be pretty familiar. This is the mistake that every new C programmer makes, right? They try to return an array, which is actually a pointer, that kind of thing. You can compile this code. It will do something. What it does depends on your optimization settings usually, but you should, this is undefined behavior. We don't want to write this in C++. This Rust code is totally equivalent. So this is the only slide where I'm going to talk very much about syntax just to get us started. We can see, for example, that taking a pointer to an int is literally exactly the same line. So that's cool. That's familiar. When we declare things, the types go on the right. The types are also optional. So I think all of the types in my slides here, I could have left out. So I'm going to include them for clarity so that, especially when we see a new type we haven't talked about before, I'll make sure to include it. But they're optional. Let is declaring new variables. It's kind of like auto in C++. dbg exclamation point. This is printing here. So this is a debug print. Exclamation point means it's a macro. We're going to use macros for printing and for asserting, but we're not going to use them for anything fancy. And so I'm not going to talk much about how macros work. It's a macro. This is a debug print. So this is just printing the dereferenced integer, which, as we know, this is equivalent code here, right? This is not allowed. So in Rust, this is going to be a compiler error. So let's see that. So my int does not live long enough, right there. Like, yeah, like that's the story, right? We have tried to take a pointer. Rust is typically going to call that a borrow to my int. We're trying to keep that borrow in a longer lived scope. Not allowed to do that. Rust sees this. This is a compiler error. So this probably isn't too surprising, and there are a lot of C++ compilers that can emit warnings in this case. They'll be able to spot examples like this. So as we move through the next few slides, we're gonna see different versions of the same problem, but we'll get progressively more interesting versions of the same problem, and we'll see how Rust tracks these more interesting problems as they grow. Let's move ahead. So here's a string view example right there. So string view is a C++ 17 type. So not everybody has gotten a chance to use it, but it's very convenient. It's sort of like a char star. So it points to some characters somewhere, but it doesn't rely on the null terminator. Instead, it knows how long the thing it's pointing to is. So it's actually a pair. It's like a char star size t pair. So it could point to a whole string. It could also point to part of a string, right? That's one of the advantages of having that size be in the view, is that you can point to a subset. You don't need the null terminator. So string view is a modern type, very convenient. And you can also implicitly convert standard string to a string view. And you see us doing that here. So this is my string is, of course, a string. So these characters here are going to get allocated on the heap. And then when we add z to it, that's going to create a new temporary string, which will do its own heap allocation. It's going to have space for the z. It's going to write the z in there as well. And then this assignment here will convert that standard string, that temporary string, to a string view. And those of us who have used string view before know that that's a problem. That's a pitfall. That's a foot gun, right? Because that's bad, because string view is basically a pointer, right? It's kind of a smart pointer in a way. It knows how long the characters are, but it's basically a pointer. It's holding a pointer into the string. And in this case, it's holding a pointer into the temporary heap allocation that immediately gets destroyed here, right? So this is a common foot gun with string view. Here, we're pointing to a temporary, and we compile this code, and when we run it, we get another address sanitizer error. So this is a heap use after free, right? So we have a dangling pointer into a heap allocation that's not around anymore. It only existed for like a fraction of that line of code. It doesn't even exist after this line is done. And so use after free, right? Same code in Rust. And I'm going to mostly skip over the difference between capital S string and what we usually call ref stir, or just stir. Other than to say that they're the same. So these are equivalent. So you've got capital S string is like standard string. It's going to have a heap allocation for your characters. And ref stir or stir is like string view. It's referring to characters that are somewhere. So that's about all we need to know. So of course, this code is going to have exactly the same problem. The conversion is explicit here. You can see this conversion to string view in this case uses a method that's explicit, but it's the same conversion. It has the same problem, and Rust catches it. In this case, the error is actually extremely specific to what's going on. This is a great error. Temporary value is freed at the end of this statement. Temporary value dropped while borrowed. A lot of people, including some core contributors on the Rust team, have put in a lot of work to make these error messages as great as they are. And I'm really grateful that they have done that. If you used Rust in like 2016, the errors were not this good. So we live in comfortable times. So Rust sees right through this problem. It knows, in particular, that ref stir, this string view type, is borrowing the string that it came from. It's tracking the lifetime of those things. It knows this doesn't work. Let's make it a little more interesting. Same problem, but now instead of having variables that don't live long enough, we're achieving the same issue by pushing into a container that lives too long. So here we push back my string, but because this is a vector of string view, this my string is implicitly converted. And of course, because it's here declared in the curlies, it doesn't live very long. And so the my vector of string views ends up holding a view into the string that is dead. And if you try to print that view, same error, right? Same issue. Mostly, actually, and I like to take a sidebar here because this is mostly the same error. It's definitely like incorrect for the same reason. But we see that asan, the address sanitizer, has given us a slightly different message here. Stack use after scope. And previously we saw heap use after free. So that might be a little surprising that this is a stack use after free, basically. And what we're seeing here is that standard string in C++ does what's called a small string optimization. So hello world is pretty short. That's not very many characters. And so it can fit into the stack size of the string class. So for short strings, standard string will decide to store them sort of in line in its own fields. Like it will like overwrite the capacity field, with just characters, right? It has this sort of alternate mode. That's the small string optimization. So here, in fact, the string view that my string was converted into is actually pointing to the stack. It's not pointing to a heap allocation. So that's kind of like an interesting fact. We will actually see a bit of this as we go forward. So this concept of the small string optimization will keep coming back as an informative example of different things. So keep that in the back of your mind. That for our purposes here, it's the same failure, right? Same issue, use after free. The Rust code is going to catch it in the same way. So we've gone back to the first error that we saw. Borrowed value does not live long enough. So what are we seeing here? As before, Rust knows that the string view here, it's actually implicitly converted into a string view. That's a deref coercion. Details don't super duper matter. But Rust, of course, knows that the string view borrows the string. We saw that before. It also knows that the push into my vector retains that borrow. So it's tracking the lifetime of that pointer or that borrow sort of across these API boundaries here. So it still sees the error, which is good. So making it a bit more interesting. Now, what we've done here is we've just added a helper function. This has factored out the pushback call into its own function, which in C++ doesn't really make a difference, right? This is exactly the same code. It's going to fail exactly the same way. So we haven't really changed anything here. We've just made a helper function. We call the helper function. It's the same deal. In Rust, it's the same story in that it still doesn't compile, right? So that hasn't changed. But the error that we get here is going to be very different. And this is going to start letting us peer into kind of how Rust does all of this. So let's look at that error. So lifetime mismatch, data flows from S into V. That's a little bit vague, I suppose, but it makes sense, right? We're trying to take our string view S and insert it into this vector V with push. So kind of sort of describes what we understand to be the problem, right? We're not, in this case, right, we're not supposed to push S into V, right? S is a reference to this short-lived string. So that error kind of makes sense. But it's very interesting that the error is in my pushback. And in fact, Rust doesn't have a problem with main at all. And we might have expected it to have a problem with main. I mean, this line is basically doing the same thing that we saw before when Rust totally had a problem with it. But here, Rust has a problem with my pushback. So to understand what's happening here, you have to know an important fact about the Rust borrow checker, which is that it only looks at individual functions in isolation when it's checking to see that they follow all the rules. So when Rust looks at my pushback, it does not ask whether my pushback is called in any funny way anywhere else. It's actually looking at it all by itself, just my pushback. And what it sees is that this push may or may not be valid, right? This push may or may not be valid. So if S does live long enough, then sure, why you could totally push it into V. But as we know, in our case, it doesn't live long enough. So this push is making an assumption. And my pushback has not made that assumption explicit. So Rust is going to say, if you want to assume things about these pointers, your function signature needs to state that assumption. So Rust hates this helper, actually. So let's see what we would have to do to this helper function to make it compile, which is to say, to make the error move out of the helper function and be an error in main, which is what we want. So in this case, we would need explicit lifetime annotations to make this work. Now, this is a little bit advanced. This is not something we would usually cover on the first day teaching Rust, much less the first hour, right? So this is planting a seed. You don't have to memorize this. This is getting a glimpse under the covers, seeing what's happening. This is the only line that's changed. So we've added this type parameter, except it's not a type, it's a lifetime, or it's a name of a lifetime, right? We've given ourselves this parameter A, tick A, and we've said effectively that this lifetime, the lifetime of the string views in the vector, and this lifetime, oops, right here, the lifetime of our new string view S, we've basically given them the same name, which is to say they basically have to live the same amount of time. It's sort of like taking a generic parameter T and having two arguments that are both T. That's just saying that it's the same type, right? This is saying that these two borrows are the same lifetime. The actual nitty-gritty technical details of what's happening here are a little bit theoretical. I think the lifetime system is technically a constraint solving system. And so if you read the spec and all that, you can get into all sorts of gory details. But most of the time, we don't have to use this at all if we're not retaining a borrow in some interesting way. And even when we do have to use this, most of the time, the way we use it is a pretty simple case where we're just saying that two things are the same, right? So we're saying the contents of this vector and the string that we're pushing into the vector, well, those things had better have the same lifetimes, which totally makes sense in this case, right? So now that we've said that, Rust is going to look at this line and it's going to see, okay, yeah, you've asked for the guarantees that you would need to make this line safe. Great, no problem. This helper function is fine, and the error has moved back into main. Right. So now the program, our program fails to compile where it should fail to compile, right? Which is good. So we're going to move on to big idea number 2 now. So this is kind of the end of big idea number 1 section. But this is a good place to pause and kind of take stock of how this lifetime system, this borrow checker thing, is kind of happening all the time. And there are reasonable defaults. So if you don't say anything about your borrows, Rust will just assume that they're all independent of each other. And as long as you don't try to retain any of them in some long-lived place, you won't have a problem. When you do try to retain them or put something in something else, and some property needs to extend beyond just the scope of this function, that property has to be explicit. So this is always being tracked across every function boundary, every type that might hold a borrow, a struct that might hold a pointer, in this case, a vector. It's being tracked everywhere. And the rules are local, right? It's a per function thing, but the property is global. So this sort of stuff, this lifetime stuff, actually pervades the entire language. The whole standard library is designed to accommodate this and to be explicit about borrows when they exist. One very common case that this sort of thing comes up is when you're creating an iterator type, right? If I'm iterating over some collection, then I have a pointer to that collection, and I'm also handing out pointers to its elements, right? In those sorts of situations, you'll see these lifetime parameters. In those sorts of situations, they're explicit when you're defining a new iterator. Using an iterator doesn't usually require them. So this pervades the language. This is kind of what are the core biggest big idea of what Rust is doing. So big idea number 2, moving right along. Mutable references are unique. No mutable aliasing. So if in the previous section, we were mostly looking at C++ examples that were bugs, right? So when asan yells at you, right, your code is bad and you should fix your code, right? So the lifetime rules often feel very helpful. They take some getting used to, and those annotations obviously take some getting used to, but they're catching real bugs that we know we shouldn't be writing. Here in big idea number 2, the mutable aliasing rule, that is the no mutable aliasing rule. This is where Rust starts to feel a bit more restrictive than what we're used to. So here we're going to see some examples of C++ code that's totally fine. This code here on the left, right, you take 2 references to the same integer, you use them both to increment the integer is 7. This code compiles, runs, passes the assert. There's nothing wrong about this code. It's maybe a little weird, but you're totally allowed to do this. You're totally allowed to take aliasing, mutable, non-const references to the same int in C++. In Rust, you are not allowed to do this. And this, especially in the beginning, as you're learning Rust, kind of tends to bite you. You will do this without thinking about it, using habits from other languages, and you'll write code like we have here. This is obviously a very contrived example, but you might try to write this, and what you'll find is, even though it was attempting to do the same thing, it kind of syntactically makes sense. This breaks the rules. Rust won't compile this code. Right? So it sees that we have borrowed the same int twice, mutably. Those borrows definitely overlap. We're kind of using them in a crisscross way. Won't compile our code. Right? So this is a pretty big restriction, and sometimes we have to jump through a few hoops to accommodate this rule. So we'll look at one more hoop in the next slide that we have to jump through, and then we'll talk about why, like what do we get for our trouble here? And the answer is 90% safety. In fact, the answer is 90% you get big idea number 1, right? It turns out that this is very closely related to big idea number 1 about references always being valid. So we'll see that. But one more quick example of jumping through hoops, because truth be told, this is something that you experience when you learn Rust. Here's another example. So we're taking a character array with 2 characters in it, taking a reference to the first element, a reference to the second element. We're using those references to make an assignment. So obviously, again, this is kind of contrived, but just to demonstrate the property here. And then so at the end of this, right, the array is BB, right? So we've taken two references into an array and we've used that to overwrite the first character. Perfectly valid C++ code. In Rust, this code does not compile. And here, we might be even more surprised than in the first case. At least in the first case, we're clearly aliasing the same integer. Here in this case, we're really, like, we know that we're not actually aliasing anything, right? Like, we know that character 0, the A, and character 1, the B, those are non-overlapping disjoint objects, right? Taking a reference to the two of them at the same time actually isn't aliasing. We know that. Here is an example of Rust not knowing that. So Rust here is sort of like saying, well, what it's saying is that you can't borrow char array twice. You can't have a shared borrow or a mutable borrow while another mutable borrow exists. So it sort of sees both of these as borrows of the whole array, which is kind of like saying it doesn't know that 0 is not equal to 1, which is like a little bit disappointing. We can sort of understand where it's coming from here because, of course, indexing it doesn't always use constants, right? We can index with variables, and when our indexes are variable at runtime, the compiler will not be able to prove that they aren't the same. So in general, the compiler has to assume that you're referencing potentially anything in the array. And in this special case, it doesn't really treat this as a special case. It could have, but it doesn't. So Rust doesn't know that we can take these two references at the same time. So in order to get this code to compile, we do have to jump through some hoops. And there are a lot of options here. So the next slide will just be kind of cherry picking a couple options to talk about. So this list on the left it's probably not comprehensive, but it's all the options I could think of for solving this problem. And there are a bunch of them. These are all strategies you could use to approach this problem, this kind of multiple references into a container, or in this case, specifically into an array. And I've listed them kind of in the order of how happily I would choose them. So, I would do, if I can get away with just use indexes, that's what I would do, right? That's my first choice. Pattern matching would be my second choice. So, just use indexes, right? If we had written, char array 0 equals char array 1, just using indexes without trying to take those references, of course, that would have compiled. So only in this contrived example where we force ourselves to use references do we run into this limitation. And in a lot of real world code, when you do run into this limitation, oftentimes the solution is actually to just slightly refactor your code to use indexes into whatever container instead of references. So that is often the solution. Pattern matching is a little bit fancy. We're not going to look at it. It does work in this case. I want to look at split at mute real quick because I think it's quite interesting. So split at mute is a method on slices. And slices are like a borrowing view. The same way string view is a view into a string, like a slice is a view into an array or a vector. So anything that is a slice or like a slice has this split at mute method. So here we have an array, and we can split at mute. So it takes an index, and everything before that index gets sort of split into one view, not copied, but sort of a pointer is taken, a pointer that knows how long it is, like the string view, called a slice. You get a slice of all the things to the left of that index, and you get a slice of all the things at that index and greater. And those two slices are returned in a tuple, which is sort of destructured here automatically. So we get these two variables that are two slices of the array, and split at mute returns mutable slices. Once we have returned these two slices, Rust knows, like, oh, they're mutable, right? So they must not alias. Rust just can flatly assume this. If we have these two variables that are mutable slices, the aliasing rule says they must not alias. So when we then go on to take references into each slice separately, we're totally fine, right? Rust is perfectly happy to let us take a mutable reference into one slice and a reference into a different slice that does not alias it. So you can think of split at mute as having kind of made the nature of the array visible to the compiler. Like the fact that indexes on the left and indexes on the right do not overlap, and references to those elements do not alias each other, right? So that fact becomes visible to the compiler here, and we can take advantage of it to make this code compile. There are many other options here. Cell and ref cell in particular are kind of fancy ninjutsu sort of borrowing trick types. And if you have, when you sit down and if you choose to learn Rust and really read the book and really play with a lot of Rust code, sort of going through each of these and seeing how they work, particularly cell and refcell, is an interesting exercise. They're very informative about how you can sort of make an escape hatch in the borrowing and mutability rules, but keep the code safe, right? We're not going to talk about those here. We're going to jump right to the my least favorite way to solve this problem is sort of writing unsafe code, conceptually skull and crossbones, right? This is sort of like writing C, it's the Wild West where the compiler is not keeping us safe anymore. And when we write unsafe code, we can commit undefined behavior. But you can use unsafe code to do things like this, to take pointers and just tell the compiler like, hey, trust me, right? Now, obviously, we would not use unsafe code in this case. That would be ridiculous. We have safe options. They work fine. But this is maybe a good opportunity to see how unsafe code kind of tends to work. So what we see here is that when we take these pointers, we use different pointer types, actually. So, here's the mutable reference, here's the shared reference, and these are getting cast here into what are called raw pointers, which they're both sides of the equal sign here are pointers, really. But the difference is that when we use references, they're participating in that lifetime system. The borrow checker knows what they are, is keeping track of them. And when we use raw pointers, they're not doing that at all. They don't have lifetimes. They're not tracked. The aliasing, mutability and aliasing rules are, if not totally gone, at least very relaxed. And as a consequence of that, we can only dereference raw pointers in an unsafe block, right? So here we're saying unsafe code, and we're only here, allowed to dereference our raw pointers, and then we're responsible for upholding all the soundness properties of the Rust memory model, which are numerous. So we don't write this code when we have a choice, but we can do this, and this does solve the problem. This does work. One higher level concept I want to describe before we move away from this slide and into right, this is all about the costs of big idea number 2, right? The hoops we have to jump through to satisfy the no mutable aliasing rule. Before we get to the benefits of that rule, one last idea I want to talk about on this slide is how does split at mute actually work on the inside? So this is a standard library method. So this is a standard library code here, and if you pull back the curtain, what you will see, you go read the implementation of the standard library, there's unsafe code in here. So split at mute is going to do pointer operations, kind of like this one. It's constructing slices instead of just returning references, but very similar. It's going to have a little bit of unsafe code in there, and it's going to check, for example, it's going to check that this index is in bounds, and if that index makes no sense, is out of bounds for the array, it'll panic. And it knows that once it's checked that that's in bounds, it's going to safely construct 2 slices that clearly don't overlap. So it knows what it's doing is safe. It does it with unsafe code. And then when it returns these references back to the caller, we're in kind of safe space again, sort of. And then the Rust compiler can see that we can use these 2 references safely. And this unsafe code inside split at mute is encapsulated, basically. So by checking all the appropriate, bounds, it is able to give us a little special superpower, but we don't have to write unsafe code. We only write safe code. We can use split at mute. Its unsafety has been constrained and encapsulated. So our program still cannot commit undefined behavior, even though we have the benefit of split at mute. So this is kind of always the goal with unsafe code in Rust. You can write it. There's a whole book about the rules. Some of the rules are still in flux, even. The formal memory model is still a work in progress. So it's not simple, but you can do it. And when you do it, we always try to wrap that unsafety in a safe API that allows safe callers to use that code and still have all the guarantees that they've always had. In practice, the main reason that you actually would reach for unsafe code is not as tricky as this. You would use it usually to call C functions. So you want to call something from the C standard library or from OpenSSL or something like that. C functions can do anything, so calling into them is always unsafe. That's actually the most common reason we use unsafe code in practice. But if you find yourself in the position of implementing fundamental data structures or methods on those data structures, you do sometimes see unsafe code there. And that's kind of how it likes to fit in to the language. So moving on from that, let's talk about what we get for all of this trouble, right? So we have to jump through all these hoops to avoid mutable aliasing. What do we get for our trouble? And 90% of that is we get safety. Yeah, we get big idea number one. But there is a 10% that's not just about safety. So here's an interesting example of how mutable aliasing affects the optimized assembly that the compiler is able to emit. So this is a Godbolt example. This is a clickable link. In fact, all the images that you see, all the screenshots you see in this presentation are clickable links. So if you get the slides, you can click on them and this will take you to Godbolt and you can play with it. So here we see the same code in C++ and Rust. We got C++ on the left here. We got Rust on the right. Here's the assembly that Clang outputs in this case. I think GCC ends up giving the same result here. And here's the assembly that Rust C, which is LLVM based, outputs here. And big red arrow, we can see that this 42 is still here. So what's going on? So we've written a simple function that is called store, and it does what it sounds like it does. It's going to store the value from source into dest. So it's taking a reference to an int and another reference to an int, and it's storing, reading through the first reference, writing through the second one, right? So this is the important line, right? It's saying dest equals source, right? That's a load and a store. But I have included this ridiculous extra line, right? Why is that there? Well, it's there for an example. Obviously, we wouldn't write this code ourselves. We wouldn't write this code by hand. Assigning twice to the same variable is pretty ridiculous. But this is, you could imagine this kind of thing might come up in the guts of the optimizer. You know, maybe it's inlined a few functions and, ripped out a few branches that it knows you're not going to take. And maybe after a few steps, you wind up with some assignments that end up being adjacent to each other. And then the optimizer can ask the question of, oh, can I remove this one? It would like to, right? The optimizer would like to remove that assignment of 42. And what we see here is that it cannot remove that in C++, but it can in Rust. Why is that? That's because in C++, these two pointers, these two references to integers, are allowed to alias. So I am allowed to call this function. If I have int x, I'm allowed to say store xx. That is valid C++ code. I can use the same reference to the same integer for both source and dest. If I were to do that, you can kind of follow the code and think about it for a few seconds. The x would wind up being 42, right? This store to dest would end up being reflected in the value of source because they are aliasing and would just be stored to dest again. So actually the second line would be a no-op in that case. So the final value of x, source and dest would be 42. So if these are allowed to alias, which they are in C++, we cannot elide that first store. It affects the observable behavior of the function. The optimizer has to respect that. It has to leave it in. It has to be defensive about the possibility that these two references might alias. That would be a weird thing to do, but the caller might do it. This is the code the compiler has to emit. In Rust, it does not have to be defensive about this because it has, big idea number two, the mutable aliasing rule. Here we have dest is a ref mute to an I32. That reference must not be aliased as long as it's alive. Right? If we have this reference, we know it's the only one. So we know that source is disjoint. They cannot be pointing to the same integer. So we know that storing to dest cannot modify source. And the optimizer is able to use that to elide the first store. So that's interesting. We're going to leave this concept all the way behind. This is only 10% of the story, but it's an interesting 10%, and I like to include it. Now we're going to talk all about safety. So here's an example of mutable aliasing causing trouble. So folks who've been writing C++ for a while have certainly run into bugs like this. What are we doing? We are pushing into a vector, and I'm pushing twice here for reasons that will become clear. And our push int twice helper function, just for the sake of an example, for some quirky reason, has decided to take the integer n that it's pushing into the vector. It's decided to take that integer as a reference, as a const int reference, which it can do. And of course, it's pushing regular ints into the vector. So these calls here will implicitly dereference that reference, but it has taken its argument by reference. Fair enough. But then we start to cause trouble, right? What do? Well, we create my vector. It's got a 0 in it. And then we take a reference to that 0. And then we call pushInt twice with that reference as n. So in this case, we've constructed an example where n and v are aliasing effectively. N is a pointer into v. This is going to be a familiar bug for a lot of people. What's going to happen here, that first call to pushback is going to, in this case, it may, in this case it does, it's going to reallocate the heap storage of this vector. And because of what we've done, that is going to invalidate the reference n. So on this second line, when n is dereferenced a second time, that's a use after free, right? Like that we have invalidated that reference. We tried to use it again, right? ASAN, heap use after free, right? So this is a very simple example of how mutable aliasing can break the first big rule. It can make existing references invalid, even though nothing has gone out of scope. It doesn't matter. This is a reference into some container. That container has been mutated. That reference is no longer valid, right? So this is where we see that big idea number 2, the no mutable aliasing rule, is a very, very important part of the safety story with big idea number 1. References are always valid. Mutable aliasing could be abused to invalidate references. So Rust is going to have to catch this, and it does. So what we see here is that the mutable aliasing rule saves us here. So Rust takes one look at this line and it says, right? It says, I can see that you're taking a mutable reference to this vector, but I know that vector is borrowed, right? I know that the vector is borrowed and these things they live at the same time. They're being given to the same function. I know you can't do that. It's interesting to notice that we did not get any errors in our helper here. So the last time we made a helper function, right? We kind of got into trouble and Rust didn't like our helper function. Here, it has no problem with this helper function, right? When Rust sees that you have a reference to an integer, it is happy to assume that that reference is always valid, right? That was big idea number 1. And so Rust is happy to assume that nothing we do will mysteriously, through side effects, invalidate this reference that we have. So this code is fine. Rust doesn't see any problem with this, and it sees a problem in the caller. And so here's an example of the no mutable aliasing rule preventing undefined behavior. It's a very aggressive rule, but it protects us in this case. This is a simple case, of course, as most of these slides are. This is a contrived example. But here's another link. This is to a YouTube video. Herb Sutter is a C++ guru. He writes a lot of books and things like that. And he also gives some great talks. And this was one of his talks at CPPCon, I think CPPCon 14. And he was talking about modern C++ style and how to use pointer types, when to use references, when to use raw pointers, when to use unique putter and shared putter. And he has a 5-minute digression into an aliasing issue that tends to come up in large code bases that use shared putter, right? If you dereference a shared putter, you get a pointer or reference to the object that it contains. And you also have some aliasing way to mess with that shared putter that your reference came from. It's possible, especially in reentrant complicated code, to invalidate that reference that you took. And so on his slide where he gives the best practices, the one slide where he gives the best practices for using pointers in C++, this is a line item on that slide. Is you have to be careful with shared putter. Never dereference potentially alias shared putters. So if you have time, click on this link, watch the talk, watch the whole talk. It's great. But this 5 minutes of the talk are especially interesting when considering big idea number 2, right? The no mutable aliasing rule. Another thing we think of when we think of mutable aliasing is, of course, threading, right? So if 2 threads are mutating the same thing at the same time without synchronizing, that's a data race, right? That's another type of undefined behavior. That's another thing that Rust needs to prevent. And so what I'll introduce on this slide is a modern multi-threading API, right? This is the automatically parallelized for each loop. And then we'll talk about a problem that this can cause. So this is the regular for loop that just iterates over a vector and increments each element. Here's the translation of that for loop into a standard for each using iterators. We have a lambda here, but this is the same. It compiles to exactly the same code as above. But in C++ 17, we can say parallelize this. That's pretty awesome, right? It's modern multi-core, really important, right? It's going to run on some hidden thread pool somewhere. It's going to use work stealing to figure out how many threads to use. And this is the modern way, right? Like this is easy multi-threading. This is great. So all the code on this slide is correct. Rust will do the same thing. You know, here we have a closure in Rust. It's exactly like the Lambda C++. It's doing the same thing. The dereference is explicit rather than implicit, but it's all the same. This is using, it's not actually the Rust standard library. It's the Rayon crate, which is kind of a de facto standard. It accomplishes the same thing here, right? Automatic, magical multi-threading with work stealing and some global thread pool. Great. But of course, when we try to do multi-threading, we run into trouble, right? We run into trouble with accidental shared mutability. And so, here in each case, I've just introduced a sum variable, right? I would like to know the sum of all the elements, and I'm already looping over the container. Why not compute the sum? Well, in the for loop, that's fine. You can totally write this code. In the serial for each, again, totally fine. What's going to happen here is our capture clause is saying capture by reference. So this mention of sum here will implicitly capture our reference to the outer variable sum. And this code works just fine. This is correct code. But when we're doing the multi-threaded version, it's not correct anymore, right? This is a data race. It's a data race because we've included the magic type that makes this multi-threaded. Now, what do we have? We have the ATM problem, right? Read my bank balance, subtract 100, write my bank balance, but 2 ATMs are doing it at the same time. We get the wrong answer, right? This is a data race. And it's not just the wrong answer, right? It's undefined behavior, and the compiler is allowed to miscompile this to do weird stuff. TSAN will complain, will yell at you for doing this. It's not just the wrong answer. So this is the footgun with multi-threading, right? And this, this is why making it really easy is great, but also tricky. Luckily, in the Rust case, it will catch this. So here we can, the error is not crystal clear because you need to know what a fun closure is, which has to do with a trait, and we're not going to have time to talk about the trait system and how generics work and all that stuff. But what it's saying is that this closure here, it's not allowed to hold mutable references to the outside, which, yeah, it better not be, because we're about to run it on a bunch of threads at the same time without any other synchronization. So Rust just catches this. It's really interesting to notice that this closure was fine. This code compiled and gave the right answer. This closure, once we start using the part or mute and sending it off to multiple threads, was not fine. Rust compiled the good code and did not compile the bad code. That's nice. How did it know, though? How does Rust know? And the answer is kind of the same as before. It's that every function in its signature has to say what its requirements are. And so if we look at the signature of these two different for each methods, the bodies don't matter. In fact, I want to get rid of them. Ignore the bodies. Just look at the signature. We see these declarations. And again, these are traits, and there's a lot going on here, and we don't have time to get into all of it, but we can see that there's a difference, right? The standard library iterator for each takes a fun mute, which intuitively is allowed to hold mutable references to the outside. Sort of, that you can imagine that that's what that trait means. And fun does not have the mute, and we can understand that to mean that it's not holding, it can only hold shared references to the outside. It cannot hold mutable ones. Right? So these functions have been explicit about their safety requirements. That's how Rust knows. That's pretty much always the story. Briefly, and then we'll move on to big idea number 3 and move semantics. So if we want this code to work in parallel, we have to synchronize it. And this is just mostly to show, just to give a quick view of how you can do the same thing in C++ and in Rust, right? If you want to synchronize this by making the integer atomic, you can do that. If you want to use relaxed atomics, that is a choice that you have. They're pretty confusing, but if you want to juggle chainsaws, or however Herbstadter describes it, you can do that. It's available in both languages. It's safe code, so go to town, right? Atomics work fine. That means that fetch add is actually, maybe surprisingly, not taking a mutable reference to sum. It's taking a shared reference. It's accomplishing mutability through a shared reference. So it's kind of an escape hatch there. There are a few of those. And this one is safe because that's how atomics work. That's how Rust knows this is safe. It's not taking a mutable reference. Of course, atomics are mostly about ints, right? So if we want to synchronize some other type, we would need to reach for a mutex. And so this is an example. Of course, here I'm still synchronizing the int, but this int here, this I32, we could imagine this was like a string or some other type, right? So mutex can synchronize anything, of course. And I can use a mutex to accomplish the same thing. So here in C++, I might use a lock guard, right? An RAII type. Its construction locks the sum lock, our mutex here, and its destruction will unlock that mutex. It's exception safe, which is great, right? We always like to use lock guards, right? Modern C++ multi-threading, we use lock guards. They're great. This is the same thing in Rust. One big difference, which I'll touch on here because it's going to come up in the last section when we try to tie everything together. Well, notice that mutex in Rust is a container type. It's like it's a container of one. so this in this case, the mutex contains the integer that it protects. And that ends up being a very important part of the safety story here. So what that means is we get a guard from the mutex that's pretty similar, but then we access the integer through the guard. So the guard here, this mutex guard of I32 type, is a smart pointer. We dereference it to get at the protected value. Again, this is a big part of the safety story. So we'll see this a little later. Keep that mutex as a container idea in the back of your mind. But the conclusion of this slide is there are ways to do this, right? I mean, the ways that would make it safe and correct in C++ also make it safe and correct and compiling in Rust. So that's nice. Okay, moving right along. Big idea number 3 is move semantics. So as with the wordy slide at the beginning, there's some familiar stuff at the top and the new big idea at the bottom. So let's walk quickly through this. In C++, we have pods, right? Plain old data types, like ints. You could also have an array of int or structures that just contain ints, things like that. I believe the technical term for this is trivially copyable. In Rust, we call that copy. That's just called copy. And a copy is a trait. You know, we've seen a few traits. We haven't really talked about how they work. It doesn't really matter here. So I'm just going to use the word copy without worrying exactly what it is. And copy is things that we can trivially copy. And so one interesting thing to note is that shared references to any type are trivially copyable, right? You can freely make multiple shared references to the same thing, and you can do that by copying an existing reference. Now, you can't smuggle those references out of their valid scope, right? The lifetime rules still apply to the copies, but you can make copies willy-nilly. It's fine. So when we have pods, when we have these trivially copyable types, when we use them, that generally involves a bitwise copy to some other location in memory. So like an assignment, x equals y. If y is an int or something, that's going to be a bitwise copy, right? Parameter passing, foo of x. It's going to be a bitwise copy of x. Returning, just, return x, right? That's a bitwise copy of the integer into the caller stack somewhere. These are all what we call by-value operations. So we're familiar with that in C. Basically everything is a by-value operation, bitwise copy. And in C++, that's also true of the pods, right? And in Rust, that's true of the copy types. Now, there are other types that are not copy, right? So standard vector is not trivially copyable in C++, and vec in Rust is not copy, right? Because of course it owns a heap pointer. It needs to be able to free that in its destructor. So if you made a bunch of copies, that would be a double free, right? That would allow aliasing, right? So these more interesting types, of course, cannot be copy. And it's interesting to note while we're here, ref mut t, the mutable reference type, is not copy, right? Because of the aliasing rule, you can't just willy-nilly make copies of a mutable reference. Even if you respect the lifetimes, you also have to respect the no mutable aliasing rule. So that leaves us with the question, okay, so when we do by-value operations on copy types, that's a bitwise copy. What are by-value operations on non-copy types? That's big idea number 3. These are moves, right? This is where Rust does moves. And when Rust does a move, it is always a destructive bitwise copy. Maybe that's surprising. We just talked about with copy types, we're making bitwise copies. It turns out that moves are bitwise copies also. So it also kind of looks like C, right? We pass some structure, some non-copy struct to a function by value. That's a bitwise copy. The difference is it's destructive. So when we do a move of a non-copy type, the source object disappears into thin air, right? The moved from value is gone, never spoken of again. In particular, the most important part of this is its destructor is never called, even when it goes out of scope, right? It doesn't go out of scope. It's just gone. So the word destructive can be a little bit confusing because it does not involve invoking the destructor. It specifically never invokes the destructor. The moved from value, if x is a vector and I say y equals x, I've moved x into y, the x value disappears into thin air and is never heard from again. That's a destructive bitwise copy. Everything works like this in Rust. It's just like in C, right? You don't tell C how to move a struct. It's just everything's a bitwise copy. Same thing in Rust. You don't tell Rust how to move an object. Everything moves with bitwise copies. And if the type is a non-copy type, that move is destructive, which is a little bit backwards, actually. So you can sort of think of it a copy is a move that is not destructive. You can kind of think about it either way. So that's big idea number 3, and that's how move semantics works. And we're going to try to move quickly through some examples of that to see what that means for code in the language. So key point here, right? So this is an example of moving a string, right? So we make a heap allocation once. One string is allocated on the heap, and then that allocation is moved to another variable, moved into a vector. Those of us who have used standard move in C++ are very familiar with this. If you haven't used standard move in C++, you can kind of skip forward through this section. It might not make a lot of sense, but feel free to stick with us. Rust is going to be the same. Here in Rust, the move is implicit. There's nothing like the standard move function. We don't have to create R value references. Any by value operation on a non-copy type is a move. The key difference here is S1 and S2, which by the end have been moved out of, are vanished, right? So their destructors never run. So we only get one string destructor running, the one that's contained inside the vec. When the vec is destroyed, that destructor runs. The others never do. So even though both sides of the slide here, they both make one string allocation on the heap, one vector allocation too. And they both free that allocation, once. So the same number of allocations in both cases, but the destructors all run in C++. So the destructors of S1 and S2 need to be no-ops, right? So the moves out of them will empty them in some way. Maybe it'll null out the pointer or something like that. So that's different default behavior. Now the next slide is just for contrast, so I can move back and forward. So moving, copying, moving, copying. So in C++, the default is copying, right? So this would make 3 string allocations over here. To get the same behavior in Rust, we use the clone method. So that says make a deep copy, whatever the type considers to be a deep copy, like the C++ copy constructor. We call that clone in Rust, and it's explicit. So these two things do the same thing, but by default, these operations in Rust are moves. Now Rust is going to be very strict here. So in C++, we can access a moved from object, and that code will compile. In Rust, we just can't do that. So in C++, when I try to print this moved from string, in this case, it prints empty string. And that makes a lot of sense. And I think all standard library implementations will also behave this way. But I don't think the standard says they have to. I think they're allowed to do whatever they want here. S1 is left in an unspecified state, but we can still use it. It's not usually advisable to do that. In Rust, we can't use it. It is vanished into thin air. Trying to use it is a compiler error, right? Use of move from value. So let's keep exploring these compiler errors. So here, same idea, but more insidious. We have a reference into something that we want to move from, right? So here we've taken a string view into S1, and then we move it. Same thing in Rust. We take a string view stir into S1, and then try to move it. This is not going to compile in Rust. In C++, it does compile. It does something very surprising. Because of the small string optimization in this case, the contents of the view appear to change. When S1 is emptied out, a null character is written into the stack space that the small string occupied. The view has changed. ASAN and UBSAN don't complain about this code. I don't think this is technically undefined behavior, but it's certainly implementation defined behavior. And we're really, it's not a good idea. Like, we're not supposed to write code like this in C++. We should not rely on what a moved from value is doing. We certainly should not retain iterators or references into them. In Rust, this doesn't compile. So cannot move out of S1 because it is borrowed. Same idea. This would probably violate big idea number 1, right? References have to always be valid. So you can't move something away, make it vanish into thin air while you have a reference to it. Here's an example that's a little bit more surprising. So here we've gone back to the moves that we saw before, but we've added a move out of the vector. So S3 tries to move out of the vector. In C++, this works fine. In Rust, this isn't going to compile, right? It's going to say cannot move out of index of vec string. So this is actually a special case of a more general limitation we'll see on the next slide. But it's interesting to think about, what if this did compile, what would it do, right? Would it leave, as it does in C++, would it leave the first element of the vector in some empty state? Well, the problem is in C++, that's a valid state to be in. But in Rust, when you move from something, it's not in a valid state anymore. It needs to disappear into thin air. It can't be destructed. We would have to tell vector never to destruct it somehow, which isn't really a thing we could do. I think the closest thing this could possibly compile into is a pop front, right? We could remove the first element of the vector, in this case, the only element, but if there were other elements, we have to like shift them down, right? And update the length. That's just about the only safe thing this code could do. And obviously popping from a vector by indexing into it would be extremely surprising. So it's for the best that Rust just doesn't compile this code. So you just can't do this. You can't move out of a vector like this. Here's the general limitation that that vector thing was a specific case of. So here, the function f is taking a reference to some string and trying to move out of that reference. Now, note, this is actually not an R value reference. This is a regular an L value reference, and which is odd. You know, it might not be a good idea to write this code in C++, but you can. You can move out of a regular reference if you want to. And so when f moves the string away, of course, S2 is going to end up being foo. That's what it means to move a string. That's, of course, reliable. S1, as we saw, is in practice going to be empty, but we're really not supposed to rely on that. So this move has happened through the reference. Rust will not let you do this. And from the perspective of G, sort of the caller, right, that makes sense, because if we passed a mutable reference to S1 into F, we would have to ask the question, when F is done, when control comes back to G, do we still have S1? You know, are we allowed to do this? And if F could just move out of S1 and leave it in the disappeared state, if F could just rip it out of time and space, well, then we certainly shouldn't be allowed to write this line. So we'd have this question of what F is going to do would be pretty problematic. So the answer in Rust is F just can't do that. So when F tries to move out of this string from behind a reference, this code doesn't compile. And it turns out that that's actually also what's going on here with the vector index in Rust. So, you know, as in C++, the indexing operation on vector works by, under the covers, returning a reference to the element that you've indexed to. And then the indexing syntax might or might not dereference that reference. It's the same story in both languages. And so this is actually effectively trying to move from behind a mutable reference, which you cannot do. There are ways to work around that. So if you want to swap, similar to standard swap in C++, if you want to swap an object across a reference, that's totally fine, because what are we doing? We're creating another string, an empty one in this case. We're replacing S1 with that string. So we've taken S1, but we've put something there that's valid. That's allowed. So in the vast majority of cases, this is an option that's available to you. You know, you can construct some default value of, you know, most regular types. In this case, the string won't even allocate. So this is a pretty cheap thing. You can totally do this. If you need to move through the reference, you can swap. Another option is to use the option type. This is an enum. It turns out this is a big and important subject in Rust, which unfortunately we don't have time to get into. But like optional in C++, the option type can be left in a none state. That's a valid instance of option. And so the take method on options leaves the source in a none state. So that's another thing you can do with any type could go here, right? You can have option of anything, as with optional in C++. If you need to be able to kind of rip out of some memory location through a pointer, making that an optional type is a general way that you can do that. And of course, with vector, of course, we do have a remove function. It's like pop front, right? So vector does support that shifting operation, right? Move out of the first element or any element and shift all the variables to the right, from the right down. That does work. So if you know you have a vector, then of course this is an option for you. But this will not be done implicitly just by indexing, which is probably a good thing. Because everything in Rust is movable, there's a convenience function that just means move this away and destroy it immediately, right? So you can do that to any type, and so the drop function is provided. It's available by default, and it just destroys the object immediately. So for something like a file, which would normally close the file in its destructor, if you want to close the file immediately, you know, in C++ you use the close method. Actually, in Rust you use the drop function. So you destroy that file. Now that does imply that you have ownership of the file, like that you have permission to move it. You know, we saw some cases where you don't have permission to move it, but as long as you have permission, that's the way to drop things, you know, other than just letting them go out of scope the normal way. One very interesting thing to note here about the drop function, if you look at its code in the Rust standard library, this is a very interesting sort of specific fact about Rust and its standard library, if you look at the code of drop, which I have pasted here into the slide, straight from the Rust standard library, you see that drop is not magic. There's no compiler magic here. It's the empty function, right? It's open curly brace, close curly brace. That's the code inside of drop. So drop is actually the empty function. It's generic over T, so you can call it with any value. But so this file is being moved by value because that's just what parameter passing does, right, for non-copy types, being moved by value into the drop function and then destroyed naturally at end of scope. Drop is the empty function. It just happens to be available in the global scope in Rust. So that's a very interesting fact that can kind of help pinpoint your intuition about how all these things work. So at a high level, wordy slide here, and I'll breeze through each of these bullets, but the longer version of this talk does go into a lot more depth about each of these. So high level difference, right? Moving in C++ is code that you might write for the type, right? The move constructor can contain arbitrary code. It can print if it wants to. And in Rust, it's not. It's always a destructive bitwise move. And that has different trade-offs for both languages. And, you know, there are some benefits to each. So in C++, for example, if a type is not supposed to be movable, that's fine. It just doesn't implement a move constructor. Mutex is an example of that because the mutex, for example, on Linux, the system calls that you use to implement mutex cannot tolerate the mutex moving in memory. C++, that just means mutex doesn't have a move constructor. There's no cost to that. In Rust, every type has to be movable, so there's a cost here. Rust has to heap allocate that mutex on Unix. Quickly, in GCC, the short string optimization is implemented by this surprisingly clever circular pointer. So the data pointer will actually point into the adjacent field of the string that is holding the short string on the stack. It'll point into that when the string is short. And so the caller, when you're reading the string or printing it or whatever, can just unconditionally dereference that pointer. You don't have to check a flag, or you don't have to have an if statement or a branch, right? So it's a branchless small string optimization, which is pretty cool. That means, though, that copying or moving a small string needs to update that pointer. So that string type in GCC's implementation is not trivially movable, which is totally fine in C++. C++ can support that. Rust cannot support that particular optimization. That's not an available choice for a safe Rust type, because the Rust move operation isn't allowed to just run arbitrary code and update some pointers as needed. So the types are not allowed to just be circular. In the vast majority of cases, you cannot make a circular pointer inside of a struct. And so this optimization is not available to the Rust standard library. So that's a cost. On the other hand, in Rust, one of the biggest benefits is kind of conceptual. So because every type is movable, Rust doesn't require a notion of constructors, right? Now we've seen constructors. We saw vec new and mutex new. You know, we've seen these things around, but it turns out that new is not a keyword. Those are just regular functions. The way you construct any type, any struct, is that you name it, you open the curly brace, you initialize all of its fields, and then you've just got an instance of the struct. It's just member-wise initialization. That's how everything works. And then if you're a new function, you just return that. And if your struct has private fields, then of course, then the new function is public. And so that's how people who aren't in your module can construct the type without violating the public-private rules. But constructors are not special. Like any other function, they might participate in privacy, but they don't do anything special other than that. They're not a kind of magical in-place operation that the compiler knows about. So it's a major conceptual simplification that we get from this. On the performance side, with vec, we talked about how with mutex being movable was like a requirement. It's like a cost that the type has to pay to meet the requirement of the language. It is. On the other side, for the user of the type, like from a container's perspective, the fact that all types are movable is like it's permission. Right? It's like a capability that you can take advantage of for performance. So what we can see is that Rust vec will always use memmove to implement a remove operation, because it's always safe to do that with any type. In C++, you'll sometimes get this optimization with like vec of int, for example. But with vector of vector, like in this case over here, we see that C++ can't perform that optimization, even though in theory it would be safe here. right? We happen to know that standard vector can be bitwise moved as long as you can erase the original, which the vector can do by updating its length, right? But the C++ compiler cannot see that here. There are proposals in C++ to define new types of annotations that might allow you to say, for example, vector is bit copyable or something like that. But current C++ can't do this optimization in this case, and Rust can. So that's a strength that Rust gets from this this all types are movable assumption. Another interesting one is that because move is destructive, you don't need to be able to represent the empty state in your type. So Rust's version of unique putter is box, and box cannot be null. It doesn't need to be. But unique putter does need to be null because you need to be able to move from it and leave it in some state that's valid to destroy. And so that's arguably, you know, not the choice that unique putter might have preferred, but it has to be that way in order to be movable. So there's strengths and benefits and drawbacks to both sides of this. In general, either of them can do anything with unsafe code or pointer magic, but for idiomatic sort of regular code, there are things that each language can do that the other actually can't. So that's move semantics. We're going to move right on. Sorry. So this is our last section. I've already gone a bit over an hour. I'm going to try to do this section in about 10 minutes. So this is putting it all together with arc mutex string. So we saw some multi-threading earlier, and that was, you know, carefully controlled multi-threading, right? The for each loop with some kind of magic parallelism. And those are threads that live on in some global pool, and we know that they're not going to keep using our data after for each returns. And so we get some simpler guarantees with that API. Here in this fairly complicated example, which I will go through line by line, we're doing ad hoc multi-threading, right? We're spawning our own threads. They live as long as they live. And if we join them here in this example, but we might not join them, they could run in the background. This is ad hoc multi-threading. This is where the rubber meets the road. So what are we doing here? So we're creating a string, and we're going to spawn 10 threads, and we're going to append some characters to the string on each of those threads, right? So in this for each loop, each time through the loop, it runs 10 times. We spawn a thread. The thread runs this lambda, which captures by reference, right? So that means that my string and my mutex are references implicitly captured by the lambda. We collect the handles in a vector, and then at the end, we loop over that vector and join the handles. So we spawn 10 threads. Each of them is appending to a string. They're being protected by a lock guard correctly. Good. And then we should see that the string has some characters 10 times when this is done. And this code is 99% correct. And this Rust code is equivalent to it. It turns out that this Rust code won't compile for a reason I'll get to in a second. We can notice that we see, again, mutex is a container. We saw that before. So instead of having two variables here, we have one. The mutex contains the string. But otherwise, this is similar, right? We get the guard. We use the guard as a smart pointer like we saw before. Right, so this is trying to do the same thing. Rust actually will not compile this code. Right? So Rust is going to say closure may outlive the current function, but it borrows my string. So Rust is worried that the caller might return and destroy my string while our threads are still running. And that would be a use after free, right? We know that we have this join loop that's going to prevent that from happening. Rust doesn't really understand that. That's like a runtime fact about our program. Rust isn't taking this into account. It's just seeing this and thinking, I don't like that. How does it know, by the way? Because we saw before that with the for each version, it was happy to take shared borrows of the stack, right? We borrowed the vector that we were looping over. I believe we did. No, the atomic, excuse me. When we had the atomic and the mutex, we borrowed those with shared borrows, and the for each version was happy. How does Rust know this version is different? Again, the bodies don't matter. Here are their function signatures. We saw this one before. Here's thread spawn. It has a static bound. So again, try to ignore syntax, but this is saying you're not allowed to give me closures that borrow things, any borrow. So there's a lot going on here, of course. There's a lot of different traits and things involved in threading, but the key message is it's all expressed through function signatures. That's how Rust knows. Before we leave this example, I want to point out that Rust is actually right to complain here. spawning a thread here and here can throw in C++, can panic. If it does panic, we never run this loop, right? We can return early, and that causes problems here. This would be a use after free. In this case, technically, the destructor of standard thread would terminate our program, so technically it's memory safe. That may not be what you expected this code to do if it happens to fail to spawn a thread. It means that we crucially depend on the declaration order of these variables, which we may not have been thinking about, but technically this code is memory safe. I called it 99%. This code is not, because it does not have the same behavior in the thread handle. It will not terminate the program. It's actually not memory safe. Rust is actually correct to complain here. So here's what the code looks like when it compiles. So we've made a change. So what we've done is we've put everything in an arc. So arc is Rust's shared putter. So here on the C++ side, we have shared putter of mutex and string. And because mutex is not a container, I'm using pair here. So we have a mutex and a string, and we just remember that they're related. So we've put those in a shared putter with make shared, and we've made the lambda capture that by value. So that means that when it captures my pair, our shared putter here, it's gonna call its copy constructor, which will increment the ref count on the shared putter. So these are all going to be, each closure is going to be referring to the same shared object on the heap. We need to use the first and second members to access the members of the pair now, but it's still doing the same thing it was before. This code compiles and it does the right thing in both languages. This is correct. This is how you get it working in Rust. And like, yeah, I mean, this is kind of a lot, right? Like, this is not simple. And a beginner trying to do ad hoc multi-threading in Rust, has to jump through a lot of hoops to get this code to compile, right? So this sort of example here is, this is why Rust has a reputation for being tricky to learn. It's like this code did not compile until we got everything perfect. It required familiarity with some library types, right? So you do have to jump through some hoops here. But it's important to remember, like, there are a lot of mistakes that we could have made in writing this code. And those mistakes in Rust don't compile. And even though jumping through hoops is not great for beginners, refusing to compile your multi-threading mistakes is a pretty good payoff. That's pretty good for beginners. So there's some trade-offs here. And actually, the rest of this talk will just be looking at slightly modified versions of this example. We only have a few more minutes. Slightly modified versions of this example where we've made mistakes. We didn't do it right, and see what errors Rust gives us. So here's the first mistake. What have I done here? In this case, I've just forgotten to use the mutex. In C++, I still created it, but I didn't instantiate a lock guard. I just forgot, right? So in C++, that's a data race. Here's thread sanitizer yelling at us. It's probably a use after free also, because the string will reallocate. So yeah, this is very easy to, depending on how big and complicated your code is, it's pretty easy to forget to take a lock. Rust is a little bit, when we have the mutex, we can't syntactically refer to its contents without acquiring a guard. So this is a little different. The equivalent in this case would be forgetting to create a mutex in the first place, trying to use the string directly. And what we'll see is that arc simply doesn't implement the operation that would require. So this ends up being kind of a simple type error. You can't extract a mutable reference from an arc. That's not its job, right? It knows that its job is to alias things, so it knows that it should not implement the deref mute operation. And this is a trait, and that doesn't really matter. But the important thing is you can't borrow the contents of an arc directly as mutable. So this is a type error. That's good. Here's another variant, right? Here I've used a shared mutex and a read-write lock in Rust. These are the same thing. So this is a lock that can allow many readers or one writer. Right? And here, by using a shared lock guard, I have taken a read lock, not a write lock, right? Oops, right? Like there's a mistake, right? So this code, because it's doing mutation, should have taken a write lock. This mutation is effectively unsynchronized. You can have many writers. You're going to get the same thread sanitizer error. It's going to crash. In Rust, same as before, the read guard that you get from the read method of the RW lock, if you meant to call write, but you forgot and you called read instead, the read guard does not implement deref mute, right? So it's the same as the arc. It knows it's not supposed to do this. It doesn't implement this operation. This code fails with a relatively simple type error. this is a link to a different talk where Louis Brandy from Facebook goes through a really subtle version of this that only really applies to C++. It turns out there's some crazy syntactic corner cases that you can run into where you think you're instantiating a lock guard and you are, but it's not actually locking anything. So if you have time, click through this. It's a fascinating talk. All the bugs in this talk are fascinating, but this link goes to the one that's relevant here. It can be surprisingly tricky to make sure you create lock guards properly all the time in C++. But this brings us to our final example. This is the last example in the talk. What have we changed? We've gone back to the regular mutex. We're instantiating the lock guard correctly. We haven't forgotten it. What are we doing here? We're smuggling out the pointer. So even though we take the lock guard, we lock the lock, while we acquire this pointer, we retain this pointer. We assign it to a longer lived location. And then we use it outside of the critical section. We use it later. You know, this is an example, but in the real world, right, maybe we've called some method with a reference to the string. Secretly, that object has stashed that reference. Some other method later happens to reuse it. Same problem. Like that's the real world version. Here we do it with curly braces so that we can see it. This is the Rust version. It's doing the same thing. Unlike the other examples, this one's not a type error. You could do this with these types, but you can't do it in this order. If we moved 9, if we swapped lines 9 and 10, this code would compile, but it doesn't compile here. So this is the last slide in the talk, and it's my favorite slide of the talk. Rust catches this error. It knows that our smuggled pointer, this is a valid line of code. You can do this with a lock guard. It knows that this pointer borrows the guard. And so when we try to destruct the guard early, it knows that we can't keep using that borrow. This code should not compile. If we had used the curly braces, this would, instead of giving us an error that we saw back in the section about moving, this would have given us the very first error we saw in the in the first slide of the talk. With the curly braces, this would be borrow outlives the thing that it's borrowing, right? Any way we try to do this, if we do it wrong, Rust catches this always. It's very interesting, I think, here to ask why other languages that have generic containers, languages like C++, don't try to make mutex a container. And I don't know all of the answers, but I think this is one of them. It's that even though you can guarantee that someone has to take a lock guard to get at the contents of the mutex, that might be a nice thing to guarantee. You can do that in C++. You cannot catch this bug. You cannot guarantee that they don't retain the pointer that they've gotten. Once they've gotten it, it's just a reference. It's just a pointer. There's no way for you to claw it back. And because Rust has a way to do that, it has the borrow checker, it has the lifetime rules, the mutex in Rust is able to express this high-level guarantee, right? You can only use this reference inside my critical section, right? Mutex is able to express that through the type system, and then Rust is able to catch all these errors, right? Rust doesn't know what a mutex is, right? All of this stuff, all these hoops that we're jumping through. Rust doesn't even really know what a thread is, right? All of these complicated things that we've done, spawning threads and a shared putter, this arc that's aliased from different threads. Rust doesn't really see any of that. All of that fades into the background, like here, and Rust sees just this simple relationship between a borrow of an object and the lifetime of that object. And Rust knows all it needs to know to make an ironclad guarantee here that our complicated ad hoc threading code is respecting all the rules. So this is it. This is tying everything together. We've hit on all the big ideas, references and their lifetimes, the no mutable aliasing rule, move semantics and how they work. I think it all kind of comes together in this example. I love this example. If this talk was too fast, which was almost the goal, I think this talk is meant to be fast. And if you liked it, but you thought it was too fast, I will link in the description to the slow version. It's about twice as long. Feel free to, you can reference back and forth, if that helps. And so hopefully one or the other version of this talk will be useful to you to try to get the big ideas of Rust to click. So thank you for listening.